As I mentioned earlier, the two key elements of pearlescent pigments that are really important are the particle size, which we just reviewed, but also the thickness of the coating applied to the particle. And so here we have a great example of how the thickness of the material has a profound effect on the color. And I've always found it fascinating that something as simple as mica and titanium dioxide can have so many different results. And this comes from a property known as thin film light interference. We all see thin film light interference every day when we walk across the street on a rainy day. And what happens when you look in a puddle of water and there's slight thin film of oil? What do you see?
Reflection, a rainbow.
And a rainbow reflection.
Mm-hmm.
Where does that rainbow of color come from? It comes from the light interference of light passing through that thin film and breaking the light into its component parts. Much like a prism breaks light into its component parts, so does a thin film of material. We see it in the oil. We see it on the shoulder of a pigeon on a bright sunny day in the park when that pigeon's shoulder glistens in many colors, or a peacock. We take advantage of that property by adjusting the thickness of the coating we apply to our pigments, and as a result we get a magical array of unique and distinctive color that comes from reflection, not absorption. Because all of our pigments, or many of our pigments, all of our interference pigments, are derived from titanium dioxide. And I've always found it fascinating. Here's a white pigment. How did it turn blue? How did it turn gold? And it's fascinating. So if we look at our presentation right here, you can see as the particle thickness gets thicker, or as the coating gets thicker, we go from a white light to a gold reflection, to a red reflection, to a blue reflection, and then a green reflection. And what's interesting, if you look at the chart, there's, on the gold reflection, there's actually a blue transmission. And this is a very interesting property, or a red reflection with a green transmission, or a blue reflection and a green and a gold transmission. So what happens with that? What does that mean? What happens if you take a yellow or gold pigment and you mix it with a blue pigment? What color will you get?
Green.
You would think, but in this case you actually get white, because the colors will cancel each other out. And it's one of the paradoxes of pearlescent pigments and interference colors. And understanding the subtractive nature of interference pigments, as well as their additive nature, because what happens if I add a blue interference and a green interference?
Turquoise?
You do get turquoise. And so you can blend them, but you can't. And it's very important to remember which ones are properly paired, because it can give you tremendous versatility in your formulation development. Here's an example of the interference colors on my arm. We've got a gold interference, a red interference, a blue interference, and a green interference. And you can see colors changing gradually depending upon the angle of light perception, and depending upon the darkness or lightness of my skin, you'll also see a dramatically different effect. And this is one of the important tools in your toolbox that the formulator truly needs to understand.
Can you please explain the difference between anatase and rutile titanium dioxide?
Thank you, Kathy. I appreciate that. Basically, there's a difference in crystallinity between anatase and rutile TiO2. When we precipitate TiO2, its natural orientation is to go to anatase. If we add a small amount of tin oxide, it will go to rutile. Why is that important? Well, as it turns out, the rutile version of TiO2 has a much more radiant, brighter effect. And so if you see a small, tiny addition of tin oxide in the CTFA name, you know that it's based on the rutile version and it's likely to have a brighter quality.